Hi everyone, my name is Andrew. I'm a postdoc at Harvard, and today I'll be talking about shared global and local structures that we can find in language model token embeddings. So imagine you're playing with your favorite language model, you're probing around, and you find some interesting and interpretable representation. But then reviewer 2 comes along and says, well, what about in Llama 5? Essentially what this reviewer is asking is how much similarity we can expect in representations across models. And a growing line of work suggests that our contemporary models are converging in terms of their representations. So for instance, a vision model and a text model might represent a concept of a blue cone similarly. But a lot of this work has been in the context of across modalities. And so in our work, we focus solely on language models. And in particular, we scope our study to just the token embedding weights. So this object, this E weight matrix, and mostly because these weights themselves already contain a ton of information, and you can already do a lot with just these weights. So I will mostly not talk about any activations or hidden states. And we compare language models within 3 different families, GPT-2, Llama 3, and Gemma 2. And so my talk will consist of 3 parts. First, I will talk about global similarities we can find across these language model or embeddings. 2, I will talk about local similarities. And lastly, I will talk about a very simple application that we can build on top of these insights. So starting with global geometry, the idea here is very simple. We're going to take our token embeddings, and we're going to compute this distance matrix D, where each element here is just comparing the similarity of 2 token embeddings, just using cosine similarity scores. So something like this. And you can think of this D matrix as capturing the relative orientations of your embeddings amongst each other. And once you have this distance matrix for, say, 2 different language models, you can simply compare how similar they are using something as simple as Pearson correlations. And so here are the results for GPT-2 when you compare small, medium, large, and X large, and you see pretty high correlations. But if you look at other models, say like Llama 3, you see some models sharing high global structure, but some of these models have near 0 correlations. So what's going on here? It turns out that some of these models have quote-unquote untied embeddings, which basically means that these models are trained to learn separate weights for embedding and unembedding those 2 sets of weights. And so if we were to repeat this procedure, but now on the unembedding weights of Llama 3, then you once again see very high global similarity. So this is for the global portion. Now if we were to talk about local geometry, we characterize local geometry 2 ways. One is with what's called locally linear embeddings, or LLEs. The other is to define an intrinsic dimension measure. So starting with LLEs, the idea here is quite simple. For each of our token embeddings, we're going to take its k nearest neighbors, and we're going to reconstruct each embedding as a weighted sum of its k nearest neighbors. So that's what this W vector is here. This is going to be a vector of length v, v being your vocabulary size, but it's going to be very sparse because only k entries are non-zero. And you can think of this W vector as capturing the local structure around each token embedding. And so once you've computed for this W vector for all of your tokens and for all of your models, then once again you can compare how similar these W vectors are across models. And so here are the results where each subplot is comparing against 2 models. And on the x-axis we have cosine similarity scores of the LLE weights, the W vectors, and on the y-axis is the percentage of tokens with a certain cosine similarity score in terms of LLE weights. And you can observe that most of the density lies above, say, 0.9, indicating that most of these tokens have very similar local structure. What's interesting here is that you can see these spikes at 0. And so what's the deal here? Well, we think what we're looking at here are what people have called undertrained tokens, aka glitch tokens. So you might remember tokens like solid gold Magikarp for GPT-2, where these are basically tokens that show up in the model's tokenizer, but never in the pre-training data. And so these tokens essentially have random vectors assigned to them during initialization. And we compare our list of identified undertrained tokens to those identified from prior work and see non-trivial overlap. The second way to characterize local geometry is to define a very simple intrinsic dimension measure. And the idea here is simple as well, where for each token embedding, we're once again going to take its k nearest neighbors, and we're simply going to run PCA on this subset of k points. We're simply going to count up the number of principal components needed to explain 95% of the variance on this local subspace, and we're going to call that number the number of principal components needed as the intrinsic dimension. What's interesting is, so here I'm showing you randomly sampled tokens as well as their intrinsic dimensions. This is with GPT-2 medium, so its external quote-unquote full dimension would be 1024. But if you look at tokens with low intrinsic dimensions, you often see very semantically coherent clusters around them. So for instance, for the token 450, you see other tokens that are multiples of 10, like 550, 850, 460. Same thing for, say, token Nissan. You see tokens like Mazda, Hyundai, Toyota, and so on. Whereas if you look at tokens with high intrinsic dimensions, you no longer see this semantic coherence, but instead you start seeing other lexical patterns. So for instance, for the token Z, you see other tokens that start with Z show up, like Z, Zag, Zig, and Zipper. This token A show seems to be a suffix that starts with A, and you see other suffixes that starts with A show up, like acebook, asys, asist, and so on. And once again, if you compare the distribution of these intrinsic dimensions across models, you end up looking, they end up having high correlations. So with that being said, the last part, in my last part, I will talk about a very simple application we can build on top of these insights, which is to transfer representations from one model to another. In particular, people have been using this term steering vector to refer to a one-dimensional vectorial representation of a concept. So for instance, people have found these representations for things like toxicity, truthfulness, sycophancy, and so on, where the idea is that if you simply add this concept representation into the model's hidden state during your forward pass, then you can elicit these concepts from the model's behavior. And often in these, I guess my slides got cut off here, but there should be a V here. But often when you do this intervention, there's this alpha hyperparameter that controls how strongly you're intervening into the model's hidden states, where the idea is that the larger this A value is, the more you're intervening and the more likely you're to see whatever target behavior you're interested in. And there are various ways to extract these steering vectors, which I won't talk about here. But imagine you have two different language models of different dimensions. And say you've gone through the trouble of extracting some steering vector for the first language model. Well, our idea is very simple. We simply take advantage of the fact that our unembedding spaces are similar. So all you have to do is learn a very simple linear map for your points in the first language model to the points in your second language model. Then you just simply have to apply this linear mapping to your steering vector, and the resulting projection is now able to steer and control your second language model. And so I'll show you some results demonstrating this. Here we're looking at a steering vector for the concept of refusal. So if you add this vector to the model's hidden states, then it's more likely to refuse the user's request. On the x-axis is that alpha hyperparameter that I was telling you about, and the y-axis is the likelihood of seeing this concept being demonstrated. And the blue dashed line is if we were to extract this steering vector from Llama 3 8B and to use it to steer and intervene the same model. Whereas the orange and green lines are if you were to extract the steering vector from a 1B model or a 3B model, transfer it to the 8B model, and then steer your 8B model. And you see a very similar trend. And you can see this across multiple concepts in the llama family. So let me try to provide at least my intuition for why this works. And essentially, we can think about what happens in the last layer, where if we think about the logits, which I like to think about as a bilinear model between the model's last hidden state and the token embeddings. Intuitively, if you just simply add your token embedding like vector to the model's last hidden state, then of course the likelihood of that sample, of that token from being sampled goes up. And interestingly, oftentimes these steering vectors, if you project them onto the model's vocabulary space, you see tokens related to the concept show up. So for instance, for this myopic steering vector, if you project it onto the model's vocabulary size, you see tokens like straightforward or simple or straight show up. Same thing if you do this with an 8B model, you see tokens like simpler, shorter, short, small, smaller show up. If you were to take this steering vector from the 8B model, transfer it to the 3B model, and then unembed it, you see tokens like straightforward, simpler, and immediate show up. Funnily enough, you can go even further. If you simply flip the direction of these steering vectors and unembed them, you see words of the opposite meaning show up, like wait, hope, delay, future. Once again, same thing with the 8B model. You see wait show up, and if you take the steering vector from the 8B model, transfer it to the 3B model, and then unembed it, you see similar words show up. So that's all I have for today. If you enjoyed this talk, then I have a similar paper for one of the workshops, so feel free to stop by, and I'm happy to take questions.